It's my pleasure to welcome Ilan to our, oh, I should ask you, is it okay if we record your talk?
Okay.
Yeah, my pleasure to introduce Ilan Hirshberg from Ben Gurion University, and he will talk to us about radius of comparison and mean dimension. So take it away, Ilan.
Yeah, sure. Thanks, Karen. It's thanks for the invitation. I think it's my 0th time being in Prague, so it's really an introducer. Yeah, so I'd like to talk about some joint work with Chris Phillips. It's actually been on the archive for a while, but I don't think I talked about this to this current audience. And so if you heard me talking about it or Chris talking about it, then my apologies, or not. I don't know, unless you want to share it again. But still, I thought it should be publicized more widely. So I'd like to start. I mean, since it's I realize not everybody's thought about a lot. I figured I'll apologize and restrict a few things and mention a few things. First of all, I'm not going to prove anything at all. So I'm going to state some things, and I'm not even going to state everything properly. I'm going to kind of give some vague statements, and I'm not even going to define everything properly. So everything is bad. And if you're angry, you can be angry at Karen for inviting me, so that's okay. And I'll talk about actions of the integers, even though most of the theorems we have actually work for either actions of general amenable groups with no restrictions, so for countable amenable groups, or maybe some mild restrictions, but way milder than being the integers. But for concreteness, let's stick to that. Okay, so let's start with mean dimension, and I'll try to kind of outline the idea. That's something which goes back a bit over 20 years. It started off in a paper of Gromov, which is kind of worth looking at. It's kind of a long paper, which I haven't read it completely. Which it underlies some general philosophy, which goes roughly as follows. Given suppose you have an invariant. Okay, think about it in the vaguest possible sense. You have a space, and even the notion of what you mean by space, you can think of as vaguely as you'd want. Okay, be a set or well, let's say topological space, but manifold, whatever you think should be suitable. Okay, and let's suppose you have an invariant. Pick your favorite invariant. Okay, now let's try to come up with a dynamical version of that invariant. Okay, so you want an invariant for dynamical systems for group actions on space, which would in some sense be some dynamical relative of that invariant. Okay, where kind of the test case you want to have in mind is pick your suppose I don't know if you see my mouse wandering around or not. If not, then I don't need to show anything. Then at least the kind of a test case would be that if you take your favorite space Y, look at the shift space, so all possible functions or sequences from the integers into Y. That has a structure of a dynamical system with a shift. Okay, that's a full shift. You want, as a test case, you want whatever invariant you have, at least under reasonable conditions, to recover the invariant of Y. Okay. And then, of course, but you want the general definition, which would apply to things which are in shifts. So maybe the kind of motivating example is entropy, right? I mean, think of the easiest, the most basic invariant you can come up with, which is simply the cardinality of the space Y. Okay, and now suppose you want to look at the shift. So now we have this Cantor set, which is the right along with the shift. So all possible bi-infinite sequences in this finite set. Right, that's already had an interesting topology. It's a Cantor set. You have a shift on that, and the topological entropy of that is roughly we have this log thing going in, but basically that recovers the cardinality of the set. Okay, so now, okay, fine. So we have this example, and then you could say, well, what if your set is infinite? Well, then the entropy won't give you anything interesting. But what if the set has some interesting topology on it? So for example, what if you want to look at the dimension of the space? I mean, can you tell apart whether can you say whether you're shifting a one-dimensional thing or a two-dimensional thing? Okay, so that was kind of broad idea of Gromov, and he had some examples which we'll mention a bit later in mind, which are very different than what we think about. Linda Chancellor Weiss shortly afterwards kind of formalized that into a notion they call mean dimension, which is based on covering dimension. And here's the definition. Okay, so let's make X a compact metric space, or and pick a finite cover. Now, a finite cover has what's called the order. So you look at we call D of U. That's D of U is the smallest order of a refinement of U. So look at all possible finite refinements of U. For each one of them, the order is simply how many overlaps you have. So for any point, you can ask how many sets, how many sets from the cover contain that point. Look at the maximum one of that. That's the order. There's a -1 there depending on convention. Okay, and so we look at the smallest order of that. That's usually the way you define dimension. Or the way you define covering dimension is you look at all possible covers and look at all possible refinements of them, right? But here, instead of looking at all possible covers, we start with one fixed cover, right? And then we start iterating that. So we take a cover, we take U, then we apply our homeomorphism to it and repeat that n times. Look at the join of those, so all the possible intersections of things from those covers, and you divide by n and you see how fast that grows. Okay, it turns out this limit exists. It grows limit and not limit, but that doesn't really matter. The limit exists, and then take the soup over all possible finite covers. Okay, so that's the definition of mean dimension. Now, and this seems to satisfy this kind of Gromov's rule of thumb. If your space you're shifting is a finite CW complex, then the mean dimension of this full shift really recovers the dimension of X. For more esoteric spaces, it doesn't quite work, but it's close. Okay, so that's this construction. Notice that this is interesting only if your space is infinite dimensional, right? If the space is finite dimensional, pretty much those things here are this D of this iterative thing is always going to be bounded by the dimension of the space, and then you divide by n, so it's going to be 0. Okay. Now that's also why it's important to take things in that particular order, because the space is infinite dimensional, so you can come up with covers which are which have as high order as you want, but you fix one and then you start iterating, and then you recover the thing you're shifting. Okay. Now this was done initially to solve problems in dynamical systems. It's certainly nothing with C-star algebras. For example, one open problem which an open problem which they basically solved was the embedding problem. We know that any compact metric space embeds in the Hilbert cube. Now you have the Hilbert cube with a shift. So you can ask, well, is this true including the shift? Can you embed it in the Hilbert cube in a way which is equivariant? And the answer is no, because the Hilbert cube with a shift has mean dimension 1, and you can easily show with trivial from the definition that if you can embed one thing into another, the mean dimension can't go down, right? So if you restrict to an invariant subset, the mean dimension can't go up. So you can come with something 2-dimensional, and you can't put it in something which is 1-dimensional. Okay, so there maybe I'll quickly mention a few other examples. You have one rich source of examples which were looked at a lot, both in C-star algebras and dynamics, is subshifts. So a simple example of a subshift is, let's say, well, suppose we have our space Y, which we're shifting, but we picked some subset in it, or some subspace, okay, Y0. And now let's suppose that X0 is a set of sequences, right? But we put some restrictions. So, for example, what I wrote was, suppose every third coordinate has to be in that smaller set. Okay, then you can show that okay, the mean. So suppose, for example, that my Y is an interval. I'm shifting it, but I'm now saying that every third coordinate has to be, let's say, in some given point or in some given discrete subset. Let's say in the endpoints. Okay. So any third thing has to fall into a 0-dimensional thing. So we think, well, okay, this is going to be more than 0-dimensional, but less than 1-dimensional, and in this case, it would indeed be 2/3 dimensional. So the thing could be a non-integer. Okay, now this simple construction where you say, well, every third coordinate has to be in Y0, that's not going to be minimal. but you can make it minimal if you put infinitely many restrictions. So that's certainly kind of a standard construction of various minimal dynamical systems, and you can get them to have arbitrary mean dimensions. Now I figured I should mention that Gromov seems to have some entirely different motivations, which I thought maybe should be publicized a bit more broadly, because I don't think, at least I haven't seen anyone working on those things from the perspective of C-star algebras. So Gromov had various kind of spaces of let's say harmonic functions on all sorts of things, which and there's some natural shift on the underlying space. The thing is very infinite dimensional, but you could recover some fine dimensional stuff out of it. So maybe just to give some sort of more concrete example, so let's look at the space of all bounded functions, real valued functions on the reals. Any bounded real valued function, you can make sense of its Fourier transform. Okay, its Fourier transform won't be a function, it will be a distribution, but you if it doesn't decay, but that makes perfect sense. So suppose we look at there a period instead of a comma. So look at the set of all those functions, such that the Fourier transform is supported in some given interval, AB. Okay, these functions have to be smooth actually, but you know, we may say many things about them. And of course, if you take something and shift it, take a time shift on it, it's not going to change the support of the Fourier transform. It's going to multiply the Fourier transform by some exponential. So so if you take that, you look at the shift operation. The shift operation is a dynamical system. I'm being, well, maybe I should have been a little bit sketchy here, because we need to look at the unit ball of this, so not all bounded functions. Okay, so I should have written like that to make it compact in a suitable weak star topology. In any event, it's known, so this doesn't quite look like a shift anymore, right? There's some, you're shifting something, but it's not some subshift. So the mean dimension of that turns out to be simply the length of the interval, b minus a. I put here quotation marks on what's written on the bottom here, because it equals up to some normalization. I mean, depending on how you do the Fourier transform, where you put the 2 pi. So you might have a factor of 2 pi if you normalize differently, but that's, let's ignore that. So that's one example. There are many. There are various other things which are there is something called Brody curves, which are certain holomorphic curves. There's some natural space on that of those things, which people in dynamics looked at, and I mean, I don't know enough about the motivation for that, but for example, simply computing the mean dimension of that seemed important enough for those people to count as an inventionist paper. So someone must think that's important, and I don't know if anyone looked at what can we say about the C-star algebraic picture there. So anyway, let's go on a review comparison. So I assume most of you might be familiar with this, but I want to go over it anyway. Okay, so we have traces on C-star algebras, which let's make them unital C-star algebras. So a trace is simply normalized positive functional with the trace condition, tau of AB is tau of BA, and okay, and of course, A is commutative, then it's simply given by integration against probability measure on the space X. Given a trace, you can define what's called a rank function, d tau, which is basically the size of the relatives of the open support as seen by tau. Okay, so the example is, well, if we take let's say A to be 3 by 3 matrices, take positive rank 2 operator, so A, right? Then what you do is you simply switch the non-zero eigenvalues to 1 and look at the trace. That's what happens, and you can tell that the trace is that this rank is 2/3, so it's right of the side of the space. For functions on the space, it simply means the measure of the open support. Okay, and you can make sense of that for arbitrary C-star algebras as follows. I mean, there are various, often it's written with a formula, but I think it's easier to understand like this. If we take positive element in the C-star algebra, then you restrict the trace to the subalgebra generated by A, which is commutative, it's just the functions on the spectrum. Then d tau of A is simply the measure of the complement of the singleton zero. There's missing curly brackets there. Okay, and you can write it explicitly with a formula, but I think that's easier to understand. Now one thing to note is if you have a trace, you can extend it to a trace on matrices over A, but what's crucial here is that the way we extend it does not preserve normalization. So if I want to extend my trace to matrices over A, the trace of 1 in the matrices would be n, not 1. Okay, and that minor issue seems to be significant. Okay, I mentioned here that we could do that for quasi-traces because someone is likely to ask, but we don't care about it now. So if you don't know what quasi-traces are, then ignore that. And if you knew and wanted to ask, then I took care of your question too. So let's move on. Okay, now if we there's this notion of Kunz subequivalence for C-star algebras, which could be defined as written here. We take two elements which are positive elements in matrices over A. We say that A is Kunz dominated by B if you can conjugate B to A by some element, not necessarily unitary, up to epsilon. Okay, and that's done in the usual way we do it for K theory, where you put things in larger matrix algebra. So if you can compare something in n by n matrices with something in k by k matrices, simply add zeros and put them in the same matrix size. Okay, now it's easy to check that if A is Kunz dominated by B, then the rank function of A is less or equal to the rank function of B. That's straightforward. Then strict comparison means that the opposite is true as well. Okay, that if you can ask, well, suppose I know that the rank function of A is dominated by the rank function of B strictly in this setting, so there's a less or equal in the first one, strictly less here. Is it true that A is subequivalent to B? Okay, now that's sometimes you have it, sometimes you don't. It's a property of C-star algebras. For phenomenon algebras, for 2-1 factors, you'll always have it. So that's one of the reasons that phenomenon algebras have fewer problems in this context. So also if you have a factor of only 0.1 trace, that's also convenient. Okay, so there's this Eliot's program essentially says that you ask whether you can classify simple separable nuclear C-star algebras by various K-theoric data, which means K-theory plus traces plus some other stuff. That was worked on for a very long time until the first counterexamples showed up, first by Rodam, then by Andrew Toms. Andrew Tom's example is somehow more instructive. I won't describe this construction, but the point is that, well, his initial example basically gave you two things which have the same Elliott invariant, but one had strict comparison, one didn't. Okay, but then if you look at it more carefully, which he did, then he turned it into some sort of invariant. I'll define it soon. Okay, so in any event, here's the situation now. Vaguely speaking, so there have been some major advances on the Elliott program in the past few decades, by an extremely long list of authors. And at this point, it's essentially complete. What does it mean? It means it's known for C-star algebras, simple separable nuclear, which have what's called finite nuclear dimension or some other regularity property, the Z stability, and satisfy what's called the universal coefficient theorem, which I won't discuss. Okay, so it's finite nuclear dimension it implies strict comparison. It's conjectured to be implied by this, and it was verified. This other implication was verified under various conditions, but it's not known in general. I think it's widely expected to be true in general, but that's still open. Now, the UCT, of course, is a different other major open problem, which doesn't really have any bearing on what I'm talking about in this lecture. So all the C-star algebras we are covering have UCT, so that's not an issue. Okay. For some reason, I copied sub-equivalence, I don't know why. Okay, so as I started saying, following this counterexample, the construction of this counterexample, Andrew Toms looked at it more carefully and turned it into a numerical invariant, which instead of saying, well, we have two examples, one has, one has strict comparison, one doesn't, he kind of realized that he can kind of measure how badly the comparison fails. And then that allowed them, for example, to construct actually an uncountable family of things which all have the same Elliott conjecture, but and are all mutually non-isomorphic because they have this extra invariant which is different. That's called the radius of comparison. Okay, so radius of comparison is defined as follows. Instead of saying, well, remember strict comparison says that if d tau of A is less than d tau of B for all tau, for all traces, then A is sub-equivalent to B. So you could ask, well, what if I give myself a little more space? Instead of saying it's less than d tau of B, I'm saying, is it less even after I add to it some constant R? And maybe that would help, right? So call the radius of comparison the infimum of R is such that it works, right? And it could be 0, which is essentially strict comparison, or positive and finite or infinite. Okay, and turns out any possible value can be achieved. Or okay, so that's the story of radius comparison. Now, of course, you might wonder, what can we maybe just take the Elliott invariant, throw in radius comparison, and classify based on that? I don't think anyone expects that to be true. So, but yeah, you could try. Okay, so let's maybe I'm not going to go through Andrew Tom's construction, so it goes back to the work of Bielatson, but try to maybe illustrate why comparison might fail. Why does it work for phonemic algebras and doesn't work for C-star algebras? And then basically goes to the theory, back to the theory of vector bundles. Okay, so let's suppose that we look at things that are very far from being simple. We simply look at vector bundles. So vector bundles, you can identify them with projections in functions from x to mn. Okay, and it doesn't really matter which trace you pick, assuming x is connected, right? It doesn't really matter which trace you pick. D tau if d tau is simply trace, right? In this context, it's a projection, right? So d tau of a projection value function or trace of that simply gives you the rank of your vector bundle. Okay. Now, so comparison from this perspective sounds a bit ridiculous, right? Because what we're asking is, suppose you have two vector bundles, let's say E and F, and suppose the rank of E is less than the rank of F. Does it mean that E is a subbundle of F? That's exactly what it means, right? And that's highly unlikely, right? That normally wouldn't happen if you have a complicated vector bundle. Although there are theorems, if you open like Hosmer's book on fiber bundles, which shows that yes, you don't have, if the rank of one bundle is less than the rank of the other, it doesn't mean that it's a subbundle of that. But if it's less by enough, then it's true. And enough is given by the dimension of the underlying space. Okay, so you can see where non-comparison comes from, because maybe now if you construct our C-star algebra as some sort of things which is a limit in some suitable sense of C of x with values in mn's, you might be able to get this non-comparison to push to the limit, and maybe it will go away. And it turns out you can control that. So sometimes it does, sometimes it doesn't. And also you can see how this kind of radius comparison is related to dimension, right? Because it means that the extra space you need to be able to stick one bundle under the other is somehow controlled by dimension. Okay, and the idea is also to try to push that forward. Okay, so now, these two things, comparison, radius comparison, and mean dimension came from completely different motivations and in different worlds, right? As I said, mean dimension came about with Gromov's idea. It was used by Leibniz advice to solve this embedding problem in dynamical systems. Nothing to do with C-star algebras. Gromov's papers has various spaces of harmonic functions or solutions to various PDEs. Really nothing no C-star algebras at all. And on the other hand, Andrew Tom's example had no dynamics in it. It was some inductive limiting intended to solve this structural problem or classification problem of Elliott. No connection to dynamics. Okay, and so, however, in 2010, Giol and Kerr had an example of came up with a minimal system, which has those kind of exotic properties, let's say, or at least things which were viewed as exotic at the time, which were discovered by Andrew Tom. So they managed to construct an example of a minimal system such that the cross product has positive rates of comparison. Okay, and when it goes back to construction to some techniques in linear advice and also the work of Elofsson, they basically used some sort of subshift and had some ad hoc construction and got it. Okay, now you could say, well, maybe that's just happens to be a coincidence, right? But it did lead to some sort of conjecture, which was made by Chris Phillips and Andrew Toms, about whether there's some sort of a mysterious connection between them. Okay, so here's what's known from this perspective. So for all things which are mentioned here below, I'm assuming that we're looking only at minimal systems. So first of all, Chris Phillips, I mean, he actually never, for some reason, published it. It's in an archive. He managed to prove that the radius comparison of the cross product is always bounded from above by 1 plus 36 times the mean dimension of X. Okay, now, of course, the 36 is obviously a silly constant. It came about because of some dynamical methods which were used. And there was some 36 there, which got improved successively over time. And you could use that to improve Chris's result. The 1 is somehow more annoying because, if it was some multiple, then that'd be great. But in particular, you would like to say that if 1 is 0, so is the other. And that doesn't give you that if you have a 1. Okay, so it may be I think he wanted to improve the balance. We never published the paper, but it's certainly accessible in archive. Now, in 2017, George Elliott and Zhuang Nu looked only at the case of mean dimension 0, and they managed to show that for those situations, the radius of comparison is 0. Okay, so if the mean dimension is 0, the radius of comparison is 0, they actually show directly that the cross product absorbs the Jiangsu algebra consortium. It's Z-stable, and therefore it has straight comparison. Okay, so a priori it's something a bit so it's actually a bit stronger a priori, although now it's known to be the same. Okay, so they also suggested some sort of connection. And more recently, about 2 years ago, Zhuang Nu managed to improve that. And he actually got that in general, the radius comparison is less or equal to half the mean dimension, which was the conjectured best bound. There are some reasons to conjecture that, and that turns out to be true for upper bound. His paper works also for Z to the D actions. Okay, so that's the situation in this direction. Notice that all those bounds go in one direction, right? The radius comparison less or equal to something involving mean dimension. So what I did with Chris is try to find systematic lower bounds, because so far there's essentially nothing. The only thing which is known is this, for all, you might think that, okay, fine, I mean, maybe the radius comparison is always 0. Well, it's not because of this one example of Giol and Kerr, but that's, we'd like something a bit more systematic. Okay, so at least at the time we worked on it, and now the situation is slightly changed, and I might say something about later on, the best lower bounds were not done in terms of a covering dimension, but in terms of something called cohomological dimension. So now it was known for dimension of CW complexes, but for more general spaces, it turns out that cohomological dimension worked better. Or at least seemed to work better at the time. So the radius comparison, it was shown by Elliott and Nu in a different paper, that the radius comparison is roughly half the mean, for just for a space, not in the dynamical context. The radius comparison of C of X is roughly half the dimension of X when dimension here means dim sub q means rational cohomological dimension. I'll say what that means, okay, in a moment. So roughly half means there's actually a formula. There's not exactly that. It's that minus something, but I don't want to write something which is too technical. It's not interesting. The exact amount. Okay. So what does rational cohomological dimension mean? I assume not everybody's thought about that. I certainly haven't until I came across this. So the idea is this. Let's suppose you want to convince me that the two-dimensional sphere is two-dimensional, but you're kind of an algebraic topologist. You only like cohomology. You don't want to talk about covering dimension. Well, then it's pretty convincing. You can tell me, well, look, I mean, the second cohomology of that's non-trivial, so it can't be less than two-dimensional, right? That's a pretty convincing argument for why it's at least two-dimensional, right? Now, of course, you can't use homotopy for that because the homotopy groups, the higher ones are non-zero either. But for cohomology, that works pretty well, right? Okay, but now suppose you want to convince me that the two-dimensional disk is two-dimensional, then that argument won't work very well because it's contractible, right? So you say, well, it looks like a point. So from the perspective of cohomology, that's zero-dimensional, right? But not quite, because you could say, well, okay, let's be a bit more subtle here. The two-dimensional disk has a boundary, right? And if we look at the cohomology relative to the boundary, so or which in this case is the same thing as collapsing the boundary to a point, then now you get a two-dimensional sphere, right? So you could say, well, okay, so suppose I take my space and I say, well, let's look at all possible closed subspaces and allow us to collapse them to a point, and look at the top cohomology of all those things. And if there's anything there which is anything non-trivial in, let's say, dimension 2, then my space has to be at least two-dimensional. Okay, so that's the definition of cohomological dimension, right? You look at all possible closed subspaces. You look at the cohomology groups. You look at the relative cohomology groups with respect to those, and look at the highest non-zero one you could possibly find. Call that the rational cohomology dimension. That's less or equal to the covering dimension, and it turns out to be the same for at least spaces which are reasonably nice, but not always. Okay, rational simply means that we need rational coefficients, and you could do that for any abelian group instead. But it turns out that in this context, rational coefficients is what you need. But that's the definition I gave. You could give for any group, and you might get different values for different groups. So there's a whole theory of that. Okay, so it turns out that rational coefficients are the ones which give what was the best bound in up until recently. So the idea was say, well, okay, if the best lower bounds we have are in terms of cohomological dimension, maybe we need to go back to Gromov's original philosophy and try to construct a notion of mean dimension which is based on cohomological dimension, not on covering dimension, right? Because the idea of Leibniz-Weiss was basically take covering dimension, kind of dynamicize that. Let's take cohomological dimension, dynamicize that, and get some sort of a mean dimensional theory based on this kind of stuff. Okay, so first of all, it didn't quite work. What we did was, in terms of looking at relative cohomology with respect to subspace, it turns out to be, for us, to be better to look at the cohomology of subspace. So it's a little bit cheating, because you say, well, okay, instead of looking at the top cohomology class, the top non-zero cohomology group of X relative to something, look at the top cohomology group, top non-zero cohomology group of some subspace. Now, with that perspective, for example, if you take two-dimensional disk, well, you could put various spheres, various circles in it, which have something non-trivial in the first cohomology group, but nothing non-trivial in the second cohomology group. So that would give you something which is off by 1. Okay, so maybe from that perspective, we think the dimension of the disk is 1, but not 2. But these differences, when we take some asymptotic thing, make no difference. So that turned out to work better. So here's roughly our definition. Given we have to look at the even integers too for technical reasons, or actually maybe not so technical, which I can maybe mention. Or so we all use even integers basically because we have to use complex vector bodies. That's essentially reason, or think of it as a complex dimension. And take your space Y. Now, and suppose you have a bunch of cohomology elements in the kth cohomology. Okay, so you could take their cup product, and let's say that let's define some notion of independence, which means that those cup product of these guys is non-zero. Okay, the motivation for that is, for example, let's suppose we take, suppose your space is a product of a bunch of spheres. Okay, a bunch of k-dimensional spheres. Okay, and so now, so you have the various projections onto spheres, pull back the generator of the cohomology class of each sphere. Okay, you can take the cup product and get something which is non-zero. But if you take the same sphere, for example, and take its cup product with itself, you're going to get zero. Right? So it's some way of telling roughly that you got things from different coordinates, right? Okay. So think of it as a notion of cohomology elements being independent. Okay, so now we use this idea to somehow look at asymptotics with respect to a dynamical system. Okay, and I'm lying here about definition because there's some technicalities which I'm hiding, but I'm not entirely lying because I'm telling you I'm lying. So start with our dynamical system and start with a K. Okay, we actually have an infinite sequence of invariants, not only one invariant. And take your closed subset Y, and pick some kth cohomology class. Okay. Now we can start iterating that, right? Because we have our dynamical system. So take your cohomology class, pull it back under the action, pull it under the action squared, and so on and so forth, right? So now we get a sequence of cohomology classes, right? So now take the first n you got, and say, well, okay, maybe they're not independent anymore in the sense, but let's look at the maximum number of independent ones among them. Okay, so maybe 90% of them are independent. Okay, and normalize by n. So look at the percentage of independent ones, and look at asymptotic of that. Take the lim sup, or not rather lim inst. They let n go to infinity. We don't know we can take a limit, so it's a lim inst. And then take a sup over all possible closed subsets Y. Okay, notice it's important. You can't assume Y is invariant or anything, because if X is if the action is minimal, for example, you don't have any non-trivial invariant subspaces. But you have to take a subspace because maybe X is contractible or something. Maybe X is a Hilbert cube. So maybe there are no interesting cohomology classes of X. You have to look at subspace. Okay. So that's basically our idea, where I'm sweeping under the rug a few technical issues. Okay, so it's not quite the definition. We need to have some cover around which controls the complexity, but that's some that'll be confusing to write here. If you care about it enough, you look at the paper, and if you don't, it won't help. Okay, so that's the idea. So with this asymptotic of how many independent elements we get some sort of a something we call the kth mean cohomological dimension. If you want to, you can look at the sup of those and call that call it the mean cohomological independence dimension in general. Okay. It turns out that actually looking at each individual invariant is more interesting than looking at the superroom, but you could do that. Okay, so is it clear hopefully it's clear what the rough idea is. Yeah, I mean, I would actually ask if you could just do it purely algebraically. Just take a ring and look at the an action of a group on a ring, and take elements and start seeing. I mean, that seems to be some invariant, some algebraic invariant of an action on the ring. But I don't know if that's interesting or not. But some algebraists asked me about that. They said, "Well, yeah, go think about that." But that's what I have to say here. So here are our theorems. So first of all, if I take a finite CW complex and look at the full shift, then this mean cohomological dimension is simply the dimension of this. There's this mean cohomological independence dimension is simply the dimension of this underlying space I'm shifting. Okay, so it means that our notion kind of meets Gromov's rule of thumb, right? So in other words, this has every right to be called mean dimension as Leibniz vice versa. Now we don't know what happens to shifts of funny things, for example, but I'll say something about this later. Now, because that's very far from minimal, there are some standard constructions of subshifts, and we get similar estimates. What I mean with similar estimates, we have some examples where they were computed exactly and we get the exact bound. but typically they don't compute the mean dimension. They only show it's bounded by something. It's more than something and less than something else. So we get the same more than something less than something else, which suggests they have to be the same thing, but we don't know how to prove it's exactly the same thing. Okay, so that's the connection to dynamics. And here I should have written the radius of comparison of the cross product. For some reason, wrote XH. But in any event, the second theorem we have is that for any k, the radius of comparison of the cross product is bounded from below by the kth cohomological independence dimension minus k over 2 minus 1. Now, the minus k over 2 is good, right? Because for various examples, if we could get rid of the 1, m sid k of xh minus k over 2 is as close as you want to half the mean dimension for various subshifts of interest. It's not quite that, but you could do that. There's some density parameter you use, and the closer the density parameter is to 1, the closer you get to the mean dimension. So in many cases, it gives us something which is nearly what's conjectured to be the optimal bound, and the upper bound found by Zhuang Niu. But we don't quite get that. The annoying thing is the minus 1, which is there for some technical reason, and it would be nice to get rid of. It's not exactly minus 1, to be more precise. It's actually what we need to do is take the we have to round down to the nearest integer, and if it's an integer, we can round down one further. So if it's just a little bit more than an integer, then great. But if it's exactly an integer, we have to go all the way down by 1. Okay, so in any event, at least in many cases of interest, in lots of subshifts which were studied, this is a positive number, and it could even be close to the conjectural bound. So this gives us a much cleaner general theory, and shows that this is not some sort of an accident that in this particular construction with Joel Currit works, but actually we have systematic lower bounds. Now a few comments, and I have one more slide and then I'll end. First of all, we don't assume any minimality here. So for the upper bounds, you actually need to assume minimality. For these bounds, actually nothing seems to work. We don't assume the action. We don't assume anything about the action. Of course, if the action is trivial, then the mean dimension is 0, but as is the mean cohomological independence dimension. But if the but they actually could have fixed points or whatever you want. It makes no difference. And secondly, this works for the main result, what I call result number 2. That works for actually for actions of arbitrary amenable groups. We can define everything, and this goes through very smoothly to that context. So for the upper bounds, the best known results are for Z to the D actions. It turns out we have lower bounds for arbitrary amenable group actions. The first result, the results we have which compare what's called M sid and mean dimension, for that we need to have some mild assumption on the group, but nothing too serious. It's good enough if it has a residually finite quotient. So it doesn't have to be residually finite. Okay, so these are the results we have, and maybe I'll just say a few words on follow-up questions, and then I'll end here. Okay, so first of all, it remains to clarify better the connection between this what we call M sid and M dim. Okay, as I said, we couldn't. It seems that they coincide for reasonably nice subshifts. I mean, we don't have a theorem they coincide, but we get the same bounds, which are gotten by the dynamicists. But first of all, there might be some funny shifts. For example, there are some bizarre spaces where the dimension is infinite and the cohomological dimension is 3. So if we take shifts based on that, God knows what happens. So maybe we don't actually know at the moment of any example where they're different. So it would be interesting to have examples where they're not the same. I mean, I'd be surprised if they're always the same, but at least to understand better when they're the same or not. So one is to understand what happens with shifts, possibly of shifts of Funning spaces. The other question, which I think is interesting, is well, what happens with those things which motivated Gromov? I mean, he's a smart guy. He seemed to be interested in various things which we don't really think about as Caesar algebras. But for example, there's a space of band limited functions. There's what I mentioned, this holomorphic curves and Brody curves. So I mean, they have a postdoc, Paul Herstedt here, who's been working on the band limited case. It's not a definite result yet, but at least based on some preliminary stuff, it looks like there is a fair chance that those two notions of mean dimension would coincide for those examples, which come from some harmonic analysis. But for more complicated cases, we don't know. And if it works for those harmonic analysis examples, those band limited cases, that would be interesting because that would imply, for example, those cross products don't have strict comparison. And I don't think anyone looked at those from the classification structure perspective. Yeah, so that's kind of one kind of open line of research to understand those things. The second thing, as I said, the second question is, well, can we go back and improve the lower bounds? In particular, we'd really like to get rid of this -1 factor. We had some vague ideas, but nothing remotely definite. And if anyone wants to think about that, go ahead. The third question is, well, okay, I mean, but the original question was still about this mean dimensional based on covering, not on cohomological dimension. So can we find lower bounds in terms of this Linear Weiss mean dimension? Now here, I should say there's some, well, I'd say preliminary development. There are no results. I spent 2 weeks visiting Chris Phillips, and we discussed that, and we thought we proved it, and then we found a mistake. So right now there's a mistaken proof that there's a connection that's pretty worthless. However, if we go back to this motivating example of the motivation for using cohomological dimension with this paper of Elliott and New, where they found lower bounds for radius of comparison of C of X in terms of the cohomological dimension of the space rather than the covering dimension. So very recently, Chris Phillips, if not published yet, managed to find lower bounds in terms of the covering dimension. So that seems to suggest that even if those two notions of MSID and MDIM are different, there's some hope of finding lower bounds in terms of the same invariant we use for upper bounds. So that's some questions which I'm currently looking at, but there are no results aside for mistakes. But mistakes are not interesting. So okay, maybe I think I have 2 minutes according to what I understand, but maybe I'll end here.
Thanks very much for that very nice talk. Do we have any questions in the audience? I am seeing hands clapping, but not hands raised. If you have a question, just feel free to unmute yourself and ask.
So maybe, okay. Okay, maybe I can ask.
You're having some mild technical issues of the multiple people zooming at once. Everyone should turn off their volume, I guess, while Ali's talking.
Ali, try now. Would you try now?
No.
One of you needs to mute. Yeah. Mute and try to speak now.
Okay, could you hear me now?
No. And then Mali, maybe you can move.
Oh, never mind. I can leave.
I think the message is being typed maybe into the chat. Is that what's happening here?
Well, okay, maybe there's some.
I think it looks like there is some typing. Maybe I can ask a quick question in the meantime. So do you have also upper bounds for MSID? Or just lower bounds?
No, I mean, unless you want to use it in a roundabout way, because in those examples where we know that MSID is roughly MDIM, then okay, you get that. But
Sure.
But at least the motivation was the upper bounds we get are in terms of I mean the best upper bounds in the commutative setting are in terms of covering dimension, and the lower bounds are in terms of cohomological dimension. So some of one is more suitable for lower bounds, one more suitable for our upper bounds, but we don't
And
have
is
any
there like an obvious reason why one is easier to find lower bounds and the other is easier to find upper bounds? Is there a
yeah, so okay, that goes into some techniques of the proof, but basically you see, and that's the reason we have even numbers. But the point is that we basically use term classes. So if you have, let's suppose they have some subspace Y in X, and it has something interesting in the kth cohomology group, okay, in the kth rational cohomology group, okay, where K is even, then you know there is you can find a vector bundle over it which has that as its kth term class, okay, for two term class. Okay, and then you could use that to somehow now the term classes can be used. Things with non-trivial term classes could be used to give you bounds essentially on some sort of rate of comparison, how far it is to how. I mean, it gives you an instruction to embedding that into a trivial bundle, or to embed trivial bundles into it, right?
right? Okay.
So once you know there's something interesting in the kth rational cohomology, you can work with it to somehow find some comparison problems, right? But it's less clear how to get upper bound with that. It shows you that you can't, let's say, put the trivial bundle into something. It doesn't tell you that you can't. It doesn't tell you the other direction.
Sure. Oh, that's interesting. Yeah.
And the other direction really comes from the dimension bound, which is similar. That if you if the dimension of the underlying space is no more than so and so, then the radius comparison is not more than so. So some of that's basically what it boils down to. And there are attempts now to try to circumvent that with lower bounds is to try to find something which does not involve term characters.
Right.
So we have to so this somehow pushes this Villotson idea as far as we can, and now we need to find some way which is not Villotson, which basically uses things with trivial term characters to try to still get lower rate of comparison bounds.
So I see Ali is apparently moving downstairs. Maybe he can ask his question as he enters his. You get a nice tour of our facilities.
Oh yeah, great.
All right, Ali. So he has written a comment that says, in the work of mu, so I guess this is about the bounding of the mean dimension. That
now I can ask a question even. So I think that in the result of Zhuang Niu, we need freeness as well. Am I right? Or meaning?
Yeah. Well, so I mean, I restricted myself to talk about action of the integers. So for action of the integers, minimal implies free. His result works also as I mentioned for z to the d, and then of course we need free in the middle. Not of course, but he needs free in the middle.
And the other question is that it seems that the result of Zhuang Niu, when mean dimension of H is 0, cannot be followed from the result of Phillips, because there is a constant.
Yeah, there's a +1.
Yeah.
Yeah. No. So there are some. I think basically Chris's works with the 1 + 36 is started off a string of improvements. Which basically the best one is the one due to Zhuang Niu. So you basically replaced the 36 by 1/2, and more excitingly got rid of the 1. I mean, I think I think we'd be happier with getting rid of the 1 and getting rid of 36, but he did both. I mean, I think there's some previous improvements which weren't even published, where basically 36 was improved, but not the 1. Yeah. But and it's conjectured to be the best possible bound. But
thank you so much for your great talk.
I have another maybe quick question that's sort of slightly off topic, but so we know these Gill and Kerr results have different radius of comparisons. That's non-zero. are there any examples of two dynamical systems where Z actions, I guess, where the cross products actually do have the same Elliott invariant, but one does not have zero radius comparison?
Oh, well, that's a good question. Actually, the quick answer is I don't know. It wouldn't surprise me if it's possible to do that. But okay, it's a good question. I assume that you have to dig more carefully into subshifts and try to control better what's going on. But these things are highly complicated. So we don't know how easy it is to control the trace spaces of those things. You could probably control the topology fairly well. You could probably make them retractable. Well, even that's not trivial, but you could probably do that. So I assume you could make sure the K theory isn't too bad, but the question is how to control the trace spaces. But I'm not sure. But it's a good question. I mean, that's actually I was very surprised if it can't be done, but it's
Yeah, I would also be surprised if it couldn't, but I was wondering if there's actually any actual examples, just out of curiosity.
Yeah, no, it's a good question. Actually, but someone to do that.
Okay, so do we have any other questions from the audience? I'm looking, I don't see anything, I think. So maybe we can just thank Ilan again for a very nice talk.
Sure, thank you.
And maybe I can quickly advertise next week, which will be again in person. 1 second.
I'll stop sharing this.
Yeah, I think I should be able to share anyway, boot you off. I have the power. Okay, share screen. Yeah, so next week we will have Becky Armstrong from Munster, and it'll be another nice C-star algebra talk about your uniqueness theorem for twisted groupoid C-star algebras. So hope to see you guys there. So thanks for coming, and thanks. It was nice to see you, Ilan.
Yeah, nice to
See everyone else
you.
next week, I guess.
Bye.